Okay, first of all, thank you for coming. Today, I'm going to make a presentation about Avail, more especially. I'm going to talk about the base layer and the light clients and how they allow decentralized scalability on Substrate and what's their importance in our infrastructure. So first of all, some words about Avail. So Avail is primarily known as a data availability layer using Substrate. We are building Avail DA because, at least in the Ethereum ecosystem too, rollups are increasingly taking a center stage. They are kind of recognized as one of the main ways to have off-chain computation, and the growth of rollups leads for more demand for data availability. Of course, we have dank sharding, proto-dank sharding, but it's kind of years of being fully ready. That's where enters DA solution, like including Avail DA. So Avail DA, that's powered by KZG validity proofs and better user experience. So definitely we'll have hundreds of general purpose and app-specific rollups or specific app chains that will all be hungry for data availability and even more. Before delving into the details, some words about myself. So my name is Ghali Ouarzazi. I'm a senior blockchain engineer at Avail, mostly on the Substrate part. I have generally 8 years of experience in development, but I joined the Substrate ecosystem in 2021. I'm with Avail since 1 year, and I work mainly on chain modular design and some other projects like Indexer, Explorer, and other typical stuff like that. So today, I'm going to talk a little bit about Avail architecture, the role of light client, and before delving into the details, I'm going to try to explain why we have chosen Substrate, what changes have we made to Substrate to make it compatible with what we want, which is data availability, at least at first, and then we'll see the light client and how they work in details. Then we'll see some future optimization and what's next for Avail in general. So, to talk about Avail architecture, let's start with the Substrate base layer. So of course, it provides the block space as any basic chain. It will provide the essential infrastructure for the chain, and will focus on allocating raw block space. So after that, we'll have the sequencing and publication. It will make sure that the data is properly sequenced, packaged into blocks, and then published while ensuring its integrity. So of course, each transaction, so we'll see some details later, but we use a sign extension. This sign extension will allow us to associate each transaction with an application ID. So this application ID will then later be used to sort all the transactions. So we will see how it is used later. But each rollup, each app chain, each application will be able to query, publish, and publish the data to query and publish their own data. Okay, so we'll also have a robust decentralized validator set. So that's thanks to the Substrate ecosystem that will sign off our published block. They won't interpret the transaction except from the base layer transaction like balance transfers and stuff like that. But for the data availability transaction, they won't interpret the transaction contained in those blocks. So that means that our data format is really flexible. Each rollup will define how to interpret its own transaction, its own data. It's completely custom and agnostic. It can be EVM, bytecode, literally anything, some text, some bytes, without even a VM at all if necessary. So this kind of represents the base layer that we have in Substrate. And above that, we'll have a peer-to-peer overlay light client network. So one light client will be able to provide a level of confidence for each block. The confidence will determine if the data are available in this block at a specific point in time for a specific amount of time. So more detail will come in a few slides. So they will use advanced verification techniques. So they used so when we generate the block, we use KZG polynomial commitments and erasure coding. And the light client use data availability sampling to allow verification while downloading only a small portion of the block. So that will be interesting. We'll show more details later. And also, like we have said before, each transaction is associated to an application ID, which means that light clients are in specific modes are able to query and get the data only specific to one rollup, app chain, application ID. So it will give high assumptions of security while still being fast and not hardware consuming. Of course, the light client, they are cross-platform. They can work on a browser, they can work on a desktop, they can work on a mobile, on a smartwatch, on anything. So it will allow us to have really a huge network, even if in reality it's not even necessary for an app chain. You can have your own sub-network of light client and it will be enough. But yeah. So now that we have seen, not really in detail, how the Avail infrastructure look like, let's talk a little bit about our choices. So why have we chosen Substrate? So theoretically, Avail want to build a flexible block space, a robust infrastructure. We want to kind of accelerate the unification of Web3 and enable modular layers to scale and interoperate in a secure and trust-minimized way. So we'll see now, before actually going to our choices, why light clients are important in Avail infrastructure. So typically, light client in general, so not really Avail specific, they enable kind of secure and decentralized access to blockchain without downloading the block content. They actually handle the headers, so they are ideal for devices with limited resources. They verify information using the block's header, the Merkle root, and they allow trust-minimized interaction. Some of their limit is that they still depend on full node for data, for consensus. They kind of contribute less to the network because they allow interaction, but they do not contribute back to the network, and they are limited to kind of basic functionalities. For Avail, our light client, they are not aimed to do the same, so they are kind of specific because our light client, we want them to give the highest data availability guarantees in a trust-minimized way. So it means that at Avail, our blocks headers, they contain all the necessary information for the data availability sampling. So any light client will be able to identify any non-availability of the data without trusting the full node. So the light client will also communicate among themselves to boost performance. So we'll see later why the peer-to-peer network is important. The light client also in this peer-to-peer network can kind of increase the block coverage. It means that the light client network can recreate the network without communicating with the full node. Of course, we leverage the Polkadot SDK for base layer operation, balance transfers, and such. So now we can say why we have chosen Substrate. So of course, Substrate is flexible. So the modularity in Substrate is baked in. It can be with the palette or anything else. Typically, we can do kind of whatever we want. For the consensus and nominated proof of stake, Babe, Grandpa, everything is like has a proven battle-tested experience and incentives, high incentives for decentralization. So we have a fast finality, so this is really important for us. The light client really take a small amount of time to kind of give a really high level of confidence for the blocks, but we have chosen to have a 20-second block time. I'll explain that a little bit more later, but typically it means that we have a 1-minute finality, which makes it kind of the fastest of all the GA layers. And to finish, it's kind of resilient. We can do a lot with Substrate if there is some nodes that are faulty, if there is a network partition, if there are forks. It can happen. It happened to us during the testnet when we had a really high peak or when we wanted to kind of update some critical parts and like 2/3 of the network had updated. We kind of had issues that kind of were sorted out thanks to Substrate resilience. So now let's delve a little bit more into the changes that we have made to Substrate. So typically, we'll start with the simple one. So for each finalized block, the light client needs some time to process the data. We'll see how much time later. And also, we have more, like for each block, at the end of the block, we do some additional process that can take some time that is kind of heavy. So we have chosen to have a 20-second block time for that. So our blocks are a little bit bigger than usual. Also, as I said before, each transaction is associated using a sign extension to an application ID. So this will allow easy retrieval from the light clients. So it means that when, for example, a rollup will send some data, it will associate it with application, for example, 1. So we'll have this information in the signature of the transaction. And to finish, we'll see how we have modified our headers. So I said a little bit before that our header contained all the information to do data availability sampling, for example. So let's take a regular block. So we can just take the header and append an extension to it. We'll see a little bit more detail in literally the next slide. So now let's take a look at what the process would look like to actually send data and how it will, what will be not the lifetime, but the flow of this data on our chain. So typically, an application will send data blobs or data bytes to Avail using an application ID. So let's say that, for example, this rollup will send the data 1 to 3 using application 1. The next rollup will send 1 to 7 using application ID 2. And again, application ID 1 will send 1 to 8, for example. So using the application ID, this data will first get sorted. So now we can see that application ID1 got sorted into the first part of this data block, if I can say. Then we'll have the application 2, and we can see that they are chunked, they are padded correctly. So now we have kind of something uniform. So now that we can take this data kind of in an agnostic way, we are going to generate commitments from it. So now we can see that we have kind of 3 rows of data. So we are going to generate KZG commitment row-wise. So we'll have 3 of them, for example. So after that, the data is going to get erasure coded. So of course, we could have erasure coded, do some erasure coding directly on the data, but we can use some homomorphic property of erasure coding, which means that erasure coding the commitments or doing erasure coding of the data itself won't really change the results. So now that it's erasure coded, we'll have extended commitments. So after that, we'll actually make a matrix of those commitments that we will put in this in the extended header that I mentioned earlier. So now that we have this extended header, the block header, and the block body containing all the data, we have this matrix which the size is dynamic, and in the end, we'll also have some additional information, so for example, the data root, but most importantly, the appendix, which kind of will say, okay, so application 1 will go from this position to this position in the matrix. The application ID 2 will go from this position to this position. And also we'll have the matrix size, which is kind of important, because the light client will need to do some random data availability sampling. We mentioned that. I'll still mention it later. But it means that we need to have the amount of cells that we'll need to retrieve from the block to be sure that we have kind of 99.99% of confidence. So typically, if the block contains, I don't know, 2 megabytes of data, we'll need, for example, 10 or 11 cells to get. But if the block is bigger than that, we'll need kind of more cells. And let's say that 30, 32 cells is kind of a high amount that will be needed. But yeah, we'll see that a little bit later in details. So now, after that, the block is going to get propagated to the network as any substrate chain. But we still have some additional process here. So how does it work? So because we have this extended header, when a block in general is broadcasted and imported, it goes through some native substrate verification, of course. We actually added a header check on top of the existing ones to match the imported header with the generated one, which means that all the validator will do some work, of course. So if we take a block and we import it normally, we'll get the block header, the imported block header, and we'll also get the body. From the body, we can make a generated header that will actually match against the imported header. And if it matches, then it means that the block is valid and that we can import it. Otherwise, it means that there is a really critical error somewhere. So of course, we also added some RPCs because, like we said before, the light client interacts with the node, with the headers. We don't want our light client to download the full block content. So we actually added some RPCs for us to be able to download small portion, small cells of the block body to kind of match them with our headers to see if everything is fine and the data are indeed available. So they kind of integrate our custom feature and can be queried by the light client. So if we have a header and the body, the light client will actually do some data availability sampling using our RPCs. So typically, if we have a light client network, so they are connected among themselves, but we'll see that later. I didn't want to mention this part now, but let's say that a second light client has queried another cell from the block body, and now a third light client will actually query the same cell. It will use some caching mechanism. Of course, it's kind of straightforward. So now that we have seen the modification we have made to our node, let's see a little bit more in details our light client. So there are kind of built using Rust and existing libraries like libp2p. So like we said, it's an overlay peer-to-peer network on top of the base layer. They do play a critical role in ensuring the data availability and validity. So in the end, we'll want our kind of end user, which are rollups and app chains, etc., to kind of handle and manage the light clients. But yeah. So they perform data availability sampling for each block using KZG commitment verification. So it means that for each commitment that we have generated previously, they will do some random data availability sampling, get some cells, match them against the commitment, which will do a cryptographic check to see if everything is fine. If there is an error, we'll detect it at this point. So they do not need to download the entire block content, and actually they really need to download the super small portion of the block. So to kinda offload the main node, so we have said that the main node are here and provide the RPCs to interact with the block body. If something is queried again and again, it will be cached using still those RPCs. But if we have like millions of light clients, we do want the light client to communicate among themselves. So if a cell is already retrieved from another light client, using this distributed hash table, we will know that this cell has already been queried. So we won't query it from the RPC, but directly from the peer-to-peer network. So the cryptographic check is going to be done to match the commitment against the sample to generate a valid proof. Okay, so like I said before, 8 to 30 samples give guarantees very close to 100%, so we can really compare this level of security to full nodes in general. So our light client, they are really aimed at data availability, of course. So to make a schema out of that, so it won't be complex, let's say that we have like 2 validators and they all have the block at 8H, for example, and we have a light client network, so we can see they are connected, and here it will be just a representation of the DHT and what we can do with it, you know. So if the light client 1 will actually, so let's say that the block at 8H is finalized, we can say that it will get the header, of course, it will get the body and say, okay, I need to run to sample one cell. It will do the cryptographic check and say that it's okay. When it's okay, it means that we'll also have this cell in the DHT. Of course, it's kind of simplified, but we'll also be able to kind of have a block replica and some of the coverage. You know, it means that we can reproduce this block at kind of this percentage. But yeah. Now, let's say that the light client 2 will do the same. So it will, of course, check the validity and do the same with the block replica. Now, let's say that the light client 3 will actually decide to sample 2 cells. But now I wanted to show the DHT and how it works in detail. So it will first try to see if the sample is not already in the DHT. So here, in this case, it's not. So it will go back to the node. Here, it will query 2 cells. Sometimes it can be a little bit more. And if the cryptographic check is, again, OK, it means that the block coverage is full. And it means that we can reproduce, that we can recreate the block. So earlier, I also mentioned some app clients, so the light client, but really for only one application ID. It also means that in this case, it will cover kind of 100% of a specific application. So it won't download random cells, but it will kind of download random cells for a specific application. Using, you know, the app index that I described a little bit later, that says, okay, so this app will go from this row to this row, for example. So if we continue a little bit to give a little bit more detail, so most of the work that was done by the light client team is to improve the peer-to-peer network because it's really important. We cannot have literally our own light client DOS our chain by millions of requests if we have millions of light clients. So this peer-to-peer network is really important. But the more light clients we have, the more the samples are going to get done in an easy manner, and the peer-to-peer network will kind of offload the main computation for all the other light clients, which means that the scalability will kind of increase. So of course, there is still the block size that's super important. But like I said, Substrate is super flexible, so that's kind of not the pain point that we have right now. It's more algorithmic and KZG and stuff like that. But the more light client we have, the bigger the blocks we can handle in the same timing. So the app client mode will only get relevant data for one application ID. So I guess that end user / rollup / app chain will be most interested by this mode, actually. And also, we sample only finalized blocks. So if we get the header, it means that it got validated kind of by the whole chain. So, but if, so the header will be kind of always valid, but if the sample won't match the commitment, we'll know directly if someone is kind of faulty and we won't use this, this RPC, we kind of will trash the sample. Okay, so right now we have described a base layer and a light client ecosystem. So that corresponds to kind of Avail DA, which will use kind of block space that will scale with light client. We use KZG, polynomial commitment, and validity proof. And we want to push Substrate even further. And so we'll have kind of another Rust kind of layer, which will be a verification hub that will kind of aggregate rollups and enable verification of proofs directly, and data will be sent to Avail. In some other term, it means that all the rollups and all the app chains that will use Avail DA will kind of have their data in the same place, which means that they will be able to settle in some interesting way and communicate among themselves in a trust minimized way. And to finish, we'll also modify Substrate to kind of have what they call Avail fusion, I would say, which is a shared security layer. So we'll literally allow like the assets of most mature ecosystem, BTC, ETH, and stuff, but even like rollups token and stuff like that to provide additional security for staking directly, for example, in the Avail chain. Okay, so now what can we like improve? Because of course, right now, for example, our RPCs, they give information about the block body, the cells that we mentioned a little bit before, but they also do some additional process. So we have a request from a light client, we'll actually get the cells, we'll do some custom process, and then we'll return this to the light client. The thing is, light client may want to do those additional process themselves, and so we can leverage this additional process directly into the light client, which will kind of lighten the work done by the RPC nodes. So that can be also interesting. So of course, enabling those specific RPCs are kind of optional for some of the nodes, you know. So right now we have also another pain point, kinda. You have seen that validators, when importing blocks, have to reproduce the whole extended header. And when we are doing KZG commitments for each rows, the block can get huge, bigger and bigger. So it means more work for the validator. Actually, it's even a little bit more complex because you have seen a matrix is generated. This matrix has columns and rows. So the rows are the number, are the commitments. So the more rows we have, the more computation heavy it will be for the validators. But the more columns we have, it means the more point in the polynomial commitment that will need to get verified by the cryptographic proof done by the light client, which means that the light client will work more. So it's kind of a trade-off between adding more work for the validator or adding more work for the light client and rollups user, I would say. But this is something that we want to improve over time, so not all the validators need to redo those verifications. Also, right now, in our KZG, how it works currently, we have row-level commitment. That's what I showed earlier. Also, openings can be at the cell level or at the row level. The thing is we can have sub-matrix level opening. So if an app ID, for example, I send some data in a block and it goes from row 1 to row 10, maybe I want to get like the commitments for all these sub-metrics directly. That can be like way easier for the node, for the light client, for literally everyone in the network, and it will be huge process gains in a way, and will even gain some storage space and stuff like that. Not really storage, but like block space. Also, like I mentioned, when I say why we have chosen Substrate, the networking improvement, so like we really want to handle more and more payload over time. That's kind of logic for a DA chain. The thing is, in the block propagation and the block import mechanism, actually the block import mechanism is quite okay, but the propagation can be an issue. So we had like a lot of transactions in our testnet, a lot of rollups, literally hundreds of millions, only one. But actually it was kind of heavy sometimes. The import time was getting a little bit higher. So that's something we kind of fiddle with the networking and the P2P parameter of the Substrate nodes, not the light client, but the Substrate nodes. And it was kind of interesting to play with that. It kind of got quite okay, but we still want to improve this process. So that's kind of it for me. So first of all, thank you for listening to me. If you have any question, I'm all ears. And of course, here are some interesting links. If some of you have their computers, you can even try the light client in the web browser right now. If I'm not mistaken, I'm not sure if I can show it right now. But since with all my presentation, I'm actually running the light client in the web, so it's not really the best. But you can see that for each node that I'm actually getting, so right now it's connected to our testnet. So don't mind the screen, but you can see that for each block, depending on the data that we have, the matrix can be pretty high. And for example, here is one random cell that actually got okay. And when we have 10 cells, well, the confidence is actually quite high. So this is a simple example of what we can do with a web light client. So I won't go into too much detail, and I will listen to you.
Is anybody having any question? Yeah.
Yeah, hi. Thanks, fantastic presentation and great animation.
Thank you.
Yeah. How exactly light clients discover full clients when they need to sample the nodes? Because you said that you're using RPCs,
Yeah.
and I can imagine it would be maybe easier if you just use the P2P layer and some discovery mechanisms. Yeah.
Definitely, actually, it used the RPCs, but before actually knowing what node to query, etc., it used the same protocol discovery like in Substrate that actually already exists. I won't be anyway able to give you that much detail about how they do this discovery because, well, like I said, I'm most in charge of the Substrate part, but I know that they are actually working on this protocol discovery. I think it's already on and developed. You know, when you also configure the light client, you can provide any type of config file. The parameters are really huge, even a little bit too much for me. But you also specify some bootstrap nodes, some stuff like that, a little bit like any Substrate node directly.
Okay, thanks.
Also, if you kind of want like more detail or kind of if you want to get involved, I think that I can point you directly to the people that will give you the most complete answer on that. You know.
Hi, you
Hello.
mentioned that you need like 8 to 30 samples to get a very high confidence.
Mm-hmm.
So like, why is it such a big range? Like, what does this, like, what are the main factors?
Yeah,
like,
of
in
course.
what situation is it 8 and what it is 30?
So let's say that in our blocks, we allow some space. We have a maximum number of bytes. It's all bounded in Substrate. So let's say that in a block, for example, in the testnet, we had maybe too much transaction, but we allowed only 2 MB in our block. So 2 MB to fit in the matrix. So you know, in Substrate, we have a lot of limiting factors. We have the weight, we have the length, but our most limiting factor for us is the matrix size. So right now, if you have like, if one cell is 32, if it's 32 kilobytes, and we have like 1024 times 1024, it means that the matrix size can go to 32 MB. I was actually in charge of pumping those numbers up, you know. So we have 2 MB in the testnet, and we tested internally like way more, and we'll try to increase it as much as we can, even if right now we are kind of okay. But what I wanted to say is that our blocks are 2 MB right now. But the reality is that not all blocks get filled to 2 MB. So if one block, for example, is filled until like 500 kilobytes, the matrix won't be 1024 times 1024. It will be actually smaller. Smaller means less sample to actually query. If the blocks are bigger, more data, more samples to query. But it's kinda so. If the block is small, we need kind of 10 samples to sample it correctly. If we have like a way bigger size, we'll still need like 30 samples. So it will kind of like the amount of sample will decrease over time, kind of over compared to the block size. Yeah.
Okay, one last question. Okay, please, brother, this guy. He came first. Okay. Thank you.
Hi, thanks a lot for
Hello.
the presentation. So
Thank
one
you.
quick question: the light Avail tools.
Sorry.
The light Avail tools
Yeah.
that says try the browser light client.
Yeah.
It's not actually running a light client on the browser. It's talking with a centralized RPC server that is connected to a network of light clients, right?
If I'm not mistaken, it's actually doing the stuff in the browser.
No, it's not. I don't think so. We can
Ah.
talk about it later.
Yeah, I'm definitely interested. Yeah.
Okay.
Yeah, thank you guys. Thank you, Ghali.
My pleasure. Thank you.